Hello students, welcome to Narayan Video College online classes. So in the last video we have discussed about the calculation of hybridization, how to calculate the hybridization for a given molecule. I have given one simple trick also, how to find out hybridization for a given molecule, and also hybridization means number of bond pairs and number of lone pairs. Clear? So that we have already done. And the next one is limitation. Till now what we have discussed, that is Vbdtd related to the what is the Vbdtd. Here limitations of Vbdtd. Yeah. So Vbdtd does not explain, and the very important points are here. Relative bond strength. The relative bond strength means what is the stability and what is the bond length and what is the bond strength, that not given, not explained by Vbdtd. And also magnetic properties. Magnetic properties of the compounds does not explained by the Vbdtd. Means we have taken one compound, just you take one compound, we have taken one compound, and that compound is a paramagnetic or diamagnetic, not explained by the Vbdtd. Clear? And next one is optical property, color. Means, so if the molecule, some molecules exhibits the color, so and why they are exhibiting color, what is the reason behind that, that not explained by what it is here, Vbdtd. So to overcome these limitations, and one theory, that is molecular orbital theory, I already mentioned. Clear? So molecular orbital theory, so that is introduced by the Hunt and Mulligan. Clear? And what is this molecular orbital theory and how these molecular orbitals will form? And first I will discuss, and after then I will give you the points. Clear? So what is that one here is molecular orbital theory. Why it is introduced? To and overcome these all limitations of VBD. VBD is, it is okay. We can use we can calculate hybridization and sometimes shape of the molecule. All this can be done by the VBD, but bond strength and magnetic properties and optical properties we cannot say by using VBD theory. So that's why molecular orbital theory. And this is introduced by which one here? Hunt's rule you have studied, that scientist. Hunt and Mulligan. So these are the two scientists introduced this MO2 theory. Clear? But it is quite similar to what is here VBD theory. So but small differences are there, and what are those, and we will discuss one by one. Yeah. So first of all, atomic orbital overlap and they lose their identity and form a new orbital. See here, they lose their identity and form a new orbitals. That is very important. Clear? And those orbitals we will call as a molecular orbitals. Those orbitals we will call as a molecular orbitals. To explain this, I will take one simple example. Simple, what it is here? Atomic orbital, they overlap or they combine, and they lose their identity during that process and form a new orbital is called as a molecular orbital. And what is that? How to explain this? Simple, I will take one simple example. Take here one frying pan. Clear? And in that one, take 2x and open that x on the frying pan, in the frying pan side by side. Clear? So just assume this is a frying pan. Clear? So what I have done here, so in this one, open 2x here. So this is one egg side by side. Open 2x one by one. So this is one egg, and this is what it is here, one egg. This is the yellow part. This is what it is here, yellow part. This is what it is here, pan. And this is what it is here, yellow part. This is what it is here, yellow part. And this is also yellow part. This is yellow part. Clear? So these are what it is, white portion of egg. This is white, and this is also what it is here, white. And this is VBD approach. How the molecule approach? One atom and another atom, they approach and overlap and form a what it is? Form a orbitals or form a bond. Clear? So that is, this is approach of which one here? VBD approach. Clear? And what is the next one? If I take here a same, again I have taken here one pan, clear, and opened two eggs and mixed thoroughly. Then what happened here? You see, this is a one yellow part of one egg, and this is another yellow part of one egg. But white parts are mixed together, and that is this is. Clear? So this is what here. These are yellow pots. Both are which one? Here, yellow pot. And this is what it is, yellow. And we mix it together. Means we mix it that one. Then what you got? This is a white. White pot is common for both. Clear? Here separate. You see, they do not lose their identity. But here these orbitals, they lose their identity. Clear? So that we will call as what it is here. And the orbital which is formed here, just assume this is a one hydrogen atom. This is one hydrogen atom, and here you are forming another hydrogen atom. Clear? So hydrogen molecule you are forming, and these new orbitals will be called as a molecular orbitals. Clear? That is the first point of what it is here, MOT. And what is the second point? You know that the electrons in the atoms present in which orbital? Atomic orbitals. In the same way, we are talking about which one? Here molecules. Clear? So the electrons in a molecules are present in various molecular orbitals. Their atom means electrons are present in atomic orbital. Molecules means the electrons are present in molecular orbitals. And very important here, same previous atomic orbital of having the same energy, they involved in the bond formation. Here also the atomic orbital of almost similar energy and proper symmetry. That is important. Proper symmetry combined to form a what it is here, molecular orbitals. Clear? Atomic orbital of almost equal energy and proper symmetry are combined to form a what orbitals here? Molecular orbitals. Clear here? Next one. So the electron density means the electrons are, attracted by in the atom. If you suppose if you take one atom, in one atom the electron density is attracted by only one nuclei, because I am talking about what it is here, only one atom. So that's why here atom center, this is a positive charge, and somewhere it is electron. The electron density is influenced by which one? Nuclei. Influenced by what? Attractions, influenced by nuclei. But if you take in this case, the electron density is influenced by two or more than two nuclei. In which one? Molecular. That is another point. Clear? And you know how many number of atomic orbitals, how many number of molecular orbitals, how many you will get, how many you will form, means how many atomic orbitals are combined, and those many molecular orbitals will be formed. Clear? Suppose two atomic orbitals combined, you will get how many molecular orbitals? Two only. In that one we will call as a bonding molecular orbital, another one we will call as a anti-bonding molecular orbitals. Clear? And very important, second, first one what it is here? One is molecular bonding molecular orbital, BMO we will call. Second one what it is? Anti-bonding molecular orbital. Always bonding molecular orbitals will have lower energy than the which one? Anti-bonding molecular. Means they will have which energy? Higher energy. They will have what is here? Higher energy. Clear? So the electron density is here distributed in what it is around the what it is here? Nuclei of the molecular orbitals. Clear? And you know this is lower energy and this is higher energy. Now these are also like orbitals only. In that one, electrons how they will fill? Same. And how electrons are filled in the atomic orbitals. Means they follow which rule? Ahbov rule, Pauli exclusion rule, Hund's rule. All here also while filling the electrons accordance with the what it is here, Ahbov principle, and obeys the Hund's rules and Pauli exclusion principle. Molecular orbitals here, bonding molecular orbitals are represented by sigma, pi, and what it is here, delta. Anti-bonding, this is what it is here, bonding molecular orbital. Anti-bonding molecular orbitals are represented by sigma star, and and what is pi star and delta. These are the main points of which one here molecular orbital theory. Clear? So what is the first? Just I will write here all the points what I have discussed. Clear one? So first of all, when two atomic orbitals they combine, they lose their identity and form a what it is here molecular orbitals. Yeah. So I will write all the points what I have explained here. That how means they lose here. If you take the VBT, they are not losing their identity, but here they lose their identity. Electrons present in the molecule, electrons are present in molecular orbital. So which orbital overlap means which atomic orbital are having the equal energy and proper symmetry, those only involved in the what it is here overlapping to form the molecular orbitals. Clear? And that is another point. Clear? And you know how many the number of molecular orbitals is equal to the number of combined atomic orbitals. One is if you two atomic orbitals combined and you will get two molecular orbitals, one molecular orbital will be called as a bonding molecular orbital, always will have lower energy and more stable, and antibonding orbital will have the higher energy. Clear? And you know molecular orbital are represented by sigma, pi and delta, and antibonding molecular orbitals are represented by what is my sigma star, pi star and delta star. I will write all these points here, just note down. So these are salient features of molecular orbital theory. I have already mentioned. And the orbital overlap, they lose their identity and form which orbitals here molecular orbitals, simply we will represent by MO. Yeah? The electrons in molecules are present in various molecular orbitals. Atomic orbitals of comparable energy and proper symmetry. What is this proper symmetry? We will discuss later. Combine to form molecular orbitals. While an electron in an atomic orbital is influenced by only one nucleus, I already mentioned. In the atomic orbital, electron is influenced by only one nucleus. But in molecular orbitals, the electrons are influenced by two or more than two nuclei, based upon how many atoms form the molecule. Clear? So that's why atomic orbitals are monocentric and molecular orbitals are polycentric. And the number of, I already mentioned, number of molecular orbitals is equal to number of atomic orbitals combined. If two atomic orbitals, A means atomic orbitals, combined and form two molecular orbitals, in that one is will be called as bonding molecular orbital BMO, and another one is anti-bonding molecular orbital AMO. And bonding molecular orbital have lower energy and hence greater stability than the corresponding anti-bonding orbital. Why bonding molecular orbitals are having lower energy also will be discussed later. Clear now? So the electron probability distribution around a group of nuclei in a molecule is given by molecular orbital. Just now only mentioned the electron density distribution is around a group of nuclei. That will be given by which one? Molecular orbitals. If you take the electron distribution is around a single nuclei in a atom is given by atomic orbitals. Molecular orbital they filled along follow all the rules here, and also bonding orbital represents sigma, pi and delta. Anti-bonding orbitals are anti-bonding is there, star will be there. Clear? So this is about what is here salient features of molecular orbital theory. Next concept is important. Formation of molecular orbitals by linear combination of atomic orbital LCAO. Clear? So according to this LCAO, orbital is a wave function. It is a wave, electron wave. Orbital is a what it is here? It is a electron wave. If waves are there, and we will represent in the form of wave functions that we have already studied in the atomic stage. Clear? Psi A we will represent with the psi. Clear? So that is psi indicates the what is amplitude of the wave, and psi square also we have discussed probability of finding electron. Clear? That only we will use here. Clear? So what is what it say LCAO, and here molecular orbitals are formed by linear combination of atomic orbital by the addition, that linear combination. That combination can be by addition or subtraction of, clear no? Subtraction of wave function of individual atomic orbitals. Wave function of which one? Individual atomic orbitals. Clear no? So that is given by which one here? So what is one here? Molecular orbitals are formed. Molecular orbitals are formed by which one? Linear combination, LCAO. Linear combination of atomic orbitals. Clear no? By what it is here? One is by addition, one is by what it is here? Addition, and the second one is by subtraction. Addition or by what it is here? Subtraction of clear no? Wave function, and that is what it is psi. Means that atomic orbitals are represented in wave function. Clear here? Wave function psi of individual orbitals. Individual atomic orbitals. Clear? So just assume, I will take here one example, that is hydrogen molecule. Clear? Hydrogen molecule means one hydrogen atom and another hydrogen atom, they combine. Clear? And form what it is here? And form. And what it is here? By addition or by subtraction, and you will get the which orbital? Molecular orbital. Suppose there is a one hydrogen atom here, there is another hydrogen atom. The wave function of one hydrogen atom is a psi A, and another hydrogen atom is what it is here? Psi B. They are combined. They are what is overlap. Then it will form which one? They will form here molecular orbitals. But how many hydrogen atoms are involved here? Two atomic orbitals. This is one atomic orbital of hydrogen and another atomic orbital of what is hydrogen. 1s. This is what is 1s, and this is also 1s. Clear? These atomic orbitals, we are talking in the form of what is wave function. Clear? They combined, by what is one time addition or one time subtraction and forms molecular orbital, and that is you will get psi molecular orbital is equal to, because here two atomic orbitals are combining, how many molecular orbitals you will get? Two only. So that's why molecular orbital is equal to what is you will get two. One is psi A plus psi B, or you can write plus or minus. By one time by addition, and another one is by what it is subtraction. Clear? So this is what it is here, and molecular orbital. Orbitals we are representing in the form of what is wave function. So that is only molecular wave function of molecular orbital is equal to wave function of atomic orbitals plus or minus, and what it is here? Atomic orbitals of A and B. Clear here? So if you get here by addition, you will get what it is here? Bonding molecular orbital. What you will get here? Bonding molecular. One is two already. One is a bonding molecular orbital and another one is a antibonding molecular orbital. So one is here bonding molecular orbital. Bonding molecular orbital is formed by the addition of wave function of atomic orbitals. Clear? That is what it is. Psi A plus psi B. Clear? Now, and here it is what is another one is antibonding molecular orbital. How it will form? Subtraction psi A plus or psi A minus what is here? Psi B. So this we will call here addition of wave function. Suppose I will simply I will take example. One hydrogen atom. We know atomic orbitals are in form of what it is wave functions. They are electron waves. Atomic orbitals are electron waves. Wave means there will be a wave function. That I will write here. This is. So this is one wave function. One is plus and another one is minus. Phases those are. Clear? So this is one hydrogen. And another hydrogen, what it is here? This is another hydrogen. Same only. I am taking another one. This is. Clear? So here plus. These are plus. These are what it is minus. and both will add. Both will what it is here? Add. Addition takes place. Addition takes place means this will be added here. Then what will happen here? What we will call here in phase, we can call in phase of orbitals. R can also be called as a addition. Addition. Clear? So this is one phase and another phase. In phase R, what it is here? Addition. R another term we can use here, constructive interference. What it is here? Constructive interference. All these are same one. Addition point means all it will be added. Then what will happen here? You will get a molecular bond, means bonding molecular orbitals. Clear, ma? So now you see this is this is what it is here. Well, you see amplitude here. This is amplitude. This we will say this is a psi A, and this is what it is psi B. This is what it is psi B. In phase R addition, R constructive interference. Then what will happen here? Amplitude is increases or not, and this we will call as a psi A plus what it is here psi B, and the orbital we will call as a what it is here bonding molecular. And if they are s orbitals, so that's why they are overlap along the internuclear axis, and this can also be called as a sigma orbitals. Sigma. Clear here? So next one what it is here, and second one, this is psi A plus psi B. This is what it is psi A plus psi B. This is positive, and this is what it is negative. Increases here, amplitude is increases. That we will call as a what is bonding molecular orbitals. Clear? So means here what it is here. The bonding molecular orbital are formed by the what it is molecular orbital. Bonding molecular orbitals are formed by addition of atomic orbitals. These are what it is orbitals only. Orbitals, you know, I said they are in the form of wave function. Clear? So bonding molecular orbitals are formed by the addition of atomic orbitals. Clear? So antibonding molecular orbital, how they formed? So I will write this is for bonding molecular orbital. Another one I will take. This is same. I will take. This is what it is. Just assume psi A. Clear? So this is plus. This is minus. This is plus. This is minus. And second one, it may be in opposite. So this is like this is minus. This is plus. Clear? Minus, this is plus. Now plus and minus will be added here. Then what will happen? Subtraction. So automatically what will happen here? So this is what it is psi B orbital of which one? Hydrogen. Then what will happen? You see, then amplitude will decrease. This is amplitude here increases, and amplitude here what it is decreases, and this is we will call as a anti-bonding molecular orbital, which is formed by what it is and subtraction of atomic orbital. So what we can write here? We can write this is psi A. This is what it is psi B. We can write out of phase. Out of phase. These are formed by what it is out of phase of atomic orbital. Or you can write by subtraction. By what it is subtraction. Or we can write what destructive interference. Destructive DE, not DI. Destructive interference. Destructive interference. Clear? So this is how this, bonding molecular orbital and anti-bonding molecular orbitals are formed. Clear here? So this is one is what it is molecular orbital, how it will be formed bonding molecular orbitals and anti-bonding molecular orbitals. And this is how it will form here. This we will consider as suppose it is sigma, then it should be what it is sigma star, or we can say anti-bonding molecular orbital. It is formed by which one? Psi A minus what it is here psi B. So this is what is atomic bonding, this is subtraction. So here antibonding molecular orbitals are formed by the subtraction of atomic orbitals. Clear? So this is about what it is here, what is bonding molecular orbitals and what is antibonding molecular orbitals. So now I have taken just example 2 hydrogens. Clear? So one hydrogen atomic orbital, another hydrogen atomic orbital. Hydrogen, you know, one electron will be present here. There is a one electron. This is which orbital one? Atomic. I simply write atomic orbitals. Atomic orbital of which one? One hydrogen. This is atomic orbital of another hydrogen. Clear? They overlap. They overlap and forms how many molecular orbitals? 2. Why? Because 2 atomic orbitals combines to form 2 molecular orbitals. So this is 2 molecular orbitals. One is, and you know, bonding molecular orbital. Another one is anti-bonding molecular, because I have written here energy. You know, I already said bonding molecular orbitals are having lower energy, anti-bonding molecular orbitals are having higher energy. Okay? So now you know that, and these 2 electrons they combine and form molecular orbitals. So where the electron will fill, here or here? So you know that they will, for while electrons are filling, they follow Aubert principle, Hund's rule, and you know, Pauli exclusive. You know that, and electrons are filled first in the lower energy orbital, then it will go to the higher energy orbital. So which one is lower energy orbital? This orbital is formed. This is what it is, bonding molecular orbital. We will consider this is sigma, because S and S they overlap along the internuclear axis. Sigma, how it will be formed? Psi A plus psi B. This we will call as a bonding molecular orbitals, and this we will call as a anti-bonding molecular orbitals. This is what it is, sigma bond. Hydrogen and hydrogen will form which bond here? Sigma bond, isn't it? That is only sigma is equal to what it is, psi A is equal to psi B. This we will call as a bonding molecular orbital. This is anti-bonding molecular orbital. It will be formed what it is, subtraction. That is only. This is sigma, which is what it is, sigma star. Where the 2 electrons will be filled? The 2 electrons will be filled here only, because first 2 electrons have to fill in the lower energy orbital. If third electron is there, it will go into that. Clear? This is simple how we have to write. This is bonding orbital. This is the anti-bonding orbitals. These are what is atomic orbitals. Clear? So I mentioned here bonding orbitals are having lower energy. Why bonding orbitals are having lower energy means, so next it is their hybridization, means how the molecular orbital will be formed. There you can very clearly understand, but I will explain what is the reason. Clear? So in the molecular orbital, bonding molecular orbitals, these are psi. Clear? The electron density is placed in between the 2 nuclei. Suppose this is hydrogen. Clear? This is hydrogen. I mentioned this is atomic here. What happened here? Electron density is placed and here between the nuclei. This is electron density. More electron density is present between the 2 nuclei. Then what will happen here? This is a nucleus means what they are? Positive charges. If there is no electron density, positive and positive will be repel each other. But what will be when they are repel each other and they will have higher energy? But what happened here? Between the 2 nuclei, electron density will be more. In case of which one? Bonding molecular orbital. And due to these electrons and repulsions will decreases. Why? Because here some wall, these electrons act like a wall between the 2 nucleus. Here positive and here positive. And due to this electron density, repulsions decreases. When repulsion decreases, energy also decreases. Energy decreases, they will have more stable. So that's why bonding orbitals will have the lower energy because of less repulsions between the nuclei. This is what it is, here. This is the electron density. Electron density. So that's why what will happen? Due to this electron density, repulsions between 2 nuclei decreases. Repulsions between two nuclei, what is what? Decreases. Repulsion decreases, automatically what will happen? What? Energy decreases. So these are in lower energy and these are in antibonding molecular orbitals are in higher energy. If you take, this is for bonding molecular orbital. If I take antibonding molecular orbitals, if you take antibonding molecular orbitals, the electron density is placed. Clear? It is not placed between the two nuclei. There are apart electron density is placed away from the nuclei. Clear? So this is suppose. Clear? So here electron density is present this side, not in between here. Between the what it is nuclei. This is positive charge and this is nuclei means which charge? Positive charge. Nuclei means which charge? Positive charge. So in case of, this is what it is here, antibonding molecular orbital. In case of antibonding molecular orbital, electron density is placed away from the place between the two nuclei. They are away from the nuclei. So that's why what will happen? Is there any electron density between here? No. So that's why they will repel each other. When they repel each other, you know what will happen here? So repulsions will be more, then energy will be high. That is the reason here. So in this case, repulsions, what it is here? Between two nuclei, what is not? Two nuclei increases. Two nuclei two nuclei increases. MEU. Two nuclei. Nice. Increases. When increases, what will happen here? Then energy increases. So that's why they will have the high bonding. So now, if I write roughly here, you see, this is one is what it is here. This is psi A, and another one is what it is. This is psi A orbital, and this is what it is psi B orbital. One hydrogen orbital, another hydrogen orbital. So they have here. One is high energy, and another one is what it is here, low energy. Clear? So this is psi A and psi B. So these are which orbital? Bonding molecular orbitals, and this is what it is, anti-bonding molecular orbitals. So you see, in this case, bonding molecular orbitals are having, this is energy. This is what it is here, energy. Clear? So if you take here, bonding molecular orbitals are having, energy of bonding molecular orbitals are, less than the energy of which one here? Atomic orbitals. Clear? So how much energy is decreased? This is the energy. Clear? This is delta, suppose. Clear? And this delta, energy decreases means what it is stabilized. So that we will call this delta is equal to stabilization energy. Which energy we will call one? This is stabilization energy. Now this is what it is. This orbital energy is increased by, suppose this is delta dash. Then what we will call this increasing energy. How much increasing energy are? Delta dash. That much increase. If energy increases, molecule will what it is unstable. So that's why this will be called as a destabilization energy. Clear? So this is about what it is here. What it is? Linear formation of molecular orbital by linear combination of atomic. Clear? Why these orbitals will have lower energy and why these orbitals will have higher energy I have explained. And next it is their combinations, types of combination. There you can very clearly understand electron density. This is about the formation of molecular orbitals by LCA. Next one is conditions for combination of atomic orbitals to form a molecular orbitals. Clear? So the first one is, as usual previous I have already discussed, the combining atomic orbital must have the same or nearly same energy. atomic orbital of the same energy or nearly same energy only overlap and form a molecular orbitals. And second one is very important. The combining atomic orbital must have the same symmetry. Means what does it mean? This is important. Means here 1s orbital has to overlap with 1s orbital only. 1s orbital will not overlap with 2s orbital. Clear? So 2s orbital will overlap with 2s orbital. This is same symmetry. Clear? So next one is s orbital will have, they have to overlap with pz orbitals only. Clear? So px orbital, s orbital, 2s and 2s. S orbital will overlap with which orbital? Only pz. Px orbital should overlap with px orbitals, and py orbital should overlap with py orbitals only, atomic orbitals only. This is what is meant here, symmetry. Clear? Having the same symmetry, then only they overlap. S orbital will overlap with s orbital. 1s orbital will not overlap with 2s. 2s, but s orbital will overlap with pz because they will have the same symmetry. Clear what is? Next, px and px orbital, they overlap. Py and py overlap. That is the what is called combining atomic orbital must have the same symmetry. That I will discuss here now. Types of molecular orbitals are there. There I will discuss overlapping. Clear? So the combining atomic orbital must overlap maximum extent. You know, maximum extent. Then bond formation will be very strong. So these are the three main points. So which these are main conditions for combination of atomic orbitals to form a molecular orbitals. And next we will discuss types of molecular orbitals. Okay, put the next heading, types of molecular orbitals. Okay, types of molecular orbitals. MO means what it is, molecular orbitals. Clear? So you know that molecular orbital of diatomic molecule are designated or represented by sigma, pi and delta. Clear, my dears? We are talking mainly for diatomic molecules. Clear? So first one here is two atomic orbitals. What is here? If two atomic orbitals, if two atomic orbitals overlap along the internuclear axis, internuclear axis, and forms which one here? Molecular orbital. Clear? So along the internuclear axis, the molecular orbital formed. Internuclear axis. Clear? So NU, this is not NEU. Sorry, previous I made a mistake. Internuclear axis and forms what it is here? Molecular orbitals called bonding molecular orbitals, or we can simply say sigma molecular or molecular orbitals. If two atomic orbitals overlap along the internuclear axis, the molecular orbital formed, the molecular orbital is called, the molecular orbital formed is called sigma molecular orbitals. Clear? The molecular orbital formed is called which orbital here? Sigma molecular orbitals. Sigma molecular orbitals, and they are symmetrical along the bond axis or internuclear axis. They are symmetrical around which one? Sigma bond I already mentioned. This is if two atomic orbitals overlap along the internuclear axis. Along the internuclear axis means which bond will form? Sigma bond only. That the molecular orbital formed is called sigma molecular orbitals. But you know, two molecular orbitals means how many molecular orbitals? Two atomic orbitals overlap means how many molecular orbitals will form? Two. One is sigma and another one is sigma star. One is what it is called sigma and another one is what it is called sigma star. That is clear? So that is, and this is sigma. And if second one, if the atomic orbital overlap sideways. Sideways means which bond form? Pi bond here. That is sideways. Then what will be? The molecular orbital formed is called pi molecular orbitals. That is the second point. If what is here? Two atomic orbitals overlap in sideways, clear? So then you know the molecular orbital formed is called what it is here? Pi molecular orbitals, clear? But they are unsymmetrical along the internuclear axis, clear? So this is means here two atomic orbitals means how many molecular orbitals should form? Two. One is a pi molecular orbital, another one is a pi star molecular orbital. Clear, guys? So this is what it is, two types. Clear? Now we will discuss here overlap of orbitals. Clear? So first of all, overlap of 1s with 1s. Clear? Overlap of 1s with 1s. How it will be? You just see. Clear? So overlap with 1s orbitals means both may have the same phase, means one hydrogen, 1s orbital and another 1s orbital may have the same phase. Same phase means one is plus, another one is plus. If both may have out of phase means one is minus and another one is minus, or one is plus and another one is minus. Clear? So now I will write here first of all this is 1s orbital. Clear? This is which phase? Positive. And this is another 1s orbital, atomic orbital, and nuclei positive, plus. Both are which one? Plus. Now and they are combined. They are what is here? Combined. Here plus and here plus. Clear? So they combine and form a which orbital? Molecular orbital. Previously we have discussed up to here, but we have not done molecular orbital. This is and plus this. This is what it is here? Molecular orbital. This we will call as which one here? Molecular orbital. This is by which one? By addition. By addition means this is a sigma 1s we will call. This is what we will call sigma 1s. This is 1s by addition. This is what it is here? Both are plus. Both are plus means what it is? Addition. By addition means which one you will get? Sigma only. Now same I will write in this way. So this is 1s and this is what is positive. And this is another one should be what it is negative. One is phase is positive, another phase is negative. Then what will happen here? They overlap. Overlap means here which overlap? Subtraction. I already mentioned previous by taking. So addition means amplitude increases and subtraction means one is plus and another one is minus. Means automatically what will happen? Amplitude is decreases. So this is only they overlap. This is what is here? Plus and this is minus. Then what happened? You see. So in this case, what happened? This is like this is one here plus. This is nuclei. This is negative. See my here. In this case, if you find out and the electron density is not present between the two nucleus, and this electron density is away from the two nucleus, so that's why this is nucleus and this is nucleus, both are positive and repulsions will be more, so that's why they will have high energy. This we will call as a sigma star 1s orbital. So that's why in case of what is here anti-bonding orbitals, energy will be high. This is what is here 1s overlap. This is by addition, this is by subtraction. Sigma 1s and sigma star 1s. In the same way, 2s also overlap in the similar way. Now, overlap of 2pz with 2pz. Next, what we will discuss now here? Overlap with what is here? 2pz. Overlap 2pz with 2pz. Overlap of 2pz with what it is not? Another 2pz orbital. Then how it will be formed? You know that this is a z orbital. Pz. This is what it is? Pz. Clear now? So this is a positive, this is a negative. Another one, what it is now? This is a positive, this is negative. They overlap. This is, and here what is now? Plus, and here plus. This is minus and minus. Now you see, positive and positive, amplitude will increases. This is molecular orbital. How we will write this is, you see, this lobe, it is decreases, and in the middle lobe increases, like this. This is, you write in this way. This is negative, this is negative. This is what it is now? Nucleus. This is a, and one nucleus, and it is a, another nucleus. This is what it is now? Positive. This is positive, means what? Electron density. Electron density is present. This is what is now? Sigma 2pz. 2pz. So this is one nucleus, and this is one nucleus. And in the middle, what is electron density will be more. Electron density will be. These are what is here. Electrons will be there, right? Overlap means this one electrons will be there. So that's why what will happen here? Electron density will be more. If electron density more between the this is one nucleus and this is one nucleus, then what will happen, man? This is a nucleus means positive. This is nucleus is positive, but electron density is there. Repulsion will be minimum. So that's why this will have lower energy. So this is bonding orbitals, bonding molecular orbital. That what it is, sigma 2pz. It is a bonding molecule. And the next one is what it is. Same pz orbital. This is pz orbital. Clear now? So this is a positive, this is a negative, and another one is a pz orbital. This is a negative, this is a positive. This is a addition. Addition means, you know, both will be positive, positive. Now positive and negative subtraction. So they overlap. Clear now? This is what is positive, negative. This is negative, and this is positive. Then what will happen here? Overlapping will take place here, bond formation takes place. No. So this side lobe will increase and here lobe will decrease. This is. So what is the molecular orbital for this is? This is what is negative. This is positive. This is positive. This is negative. Clear? So this is what it is, center. Nucleus. This is what it is, nucleus of pz orbital. Another nucleus of another pz orbital. Clear? Is there any electron density here? No, there is no electron density. Nodal plane we will say. Clear? So that's why electron density is this side, and here also electron density is this side. There is no electron density between these two nucleus. So repulsion will be more and the energy will be higher. This is about what it is, overlap of 2pz with 2pz. 2pz involved. Which one? Because nuclear axis I have taken, we will take considered as a z axis. So that's why overlapping takes place along the internuclear axis. Then you will get the which one? Sigma 1, sigma 2pz, and this is sigma star 2pz. In the same way, overlapping of 2px, overlap of 2px with another 2px, that also we will discuss here how it will be. Clear? Side overlapping. Side overlapping means which orbital will form? Pi orbital. Clear? That also we will discuss. Overlap of. Clear? So it is overlap of 2px with another 2px. So how which molecular orbitals? These all are forming what it is, molecular orbitals here. Clear? So now I have taken here 2px. This is what it is here, 2px. Clear? So this is a positive, this is a negative. I will take another 2px. Same here. This is what it is now, 2px, and here positive and negative. So they overlap. Addition, because both are what it is now. You see. This is clear. Positive, positive. Here what it is now? Negative and negative. Clear? So this is which one? Addition only. But overlapping is which one? Sideway overlapping or end-to-end overlapping? Sideway. Then which orbital you will get? Pi orbital. Clear? You will get here pi molecular orbitals. So that it is, you know, here it is in the nuclear axis. And here electron density is this is above and below the plane. This is what it is one electron density. This we will call as a what it is one here pi 2px. This is one nucleus and this is another nucleus. Clear? So this is a pi bond. So this we will call as pi 2px. Clear? In the same way, if you take this is 2px and another one is 2px. This is what is 2px. Another one is 2. Why I am saying only 2px with 2px? I already said same symmetry orbitals only overlap each other. 1s means 1s, 2s means 2s, 2pz means 2pz, and 2px means 2px only. So here one is positive, negative, negative, positive. Then overlap, side wave overlapping only here. But you know it is side wave overlapping, but here plus and minus, plus and minus. Then how this diagram? These lobes will increase, they will ripple like this. Here which one is there? Positive, and this is what it is, negative. This is negative, this is positive. So clear now? Two nodal planes we have. Clear? So this we will call as a pi star. What it is here? 2px. In the same way, if you take 2py, you will get pi 2py and you will get pi star 2py. And this is what it is here? Overlapping out. So that's why what I want to say here. If you take this is bonding molecular orbitals and these are what is anti star is there anti-bonding molecular orbital. In case of anti-bonding molecular orbital, electron density not located are not placed between the place of two centers. It is away from the centers. So that's why and this is nucleus, nucleus both are positive. So repulsions will be more higher energy here. But you can see here. Two nucleus are there, between these two nucleus electron density will be there, so repulsions will be less, so energy will be low. So this is about what it is here, overlapping are types of molecular orbitals. So here difference between bonding orbital and anti-bonding orbital. Just what we have discussed those points only, sometimes they are asking this question. So they are formed by addition of atomic orbitals. That I already mentioned sigma is equal to psi a plus psi b, and these are what it is. These are formed by the subtractive. You know, these are sigma star is equal to psi a minus what it is psi b. Electron density increases in the region between the nuclei of bonded atom. I already said electron density is located in between the in the center of the two atoms. So that's why, and these orbitals will have lower energy here. But here electron density decreases in the region between the nuclei of bonded atom. Electron density is not in between the nuclei of bonded atom, away from the nuclei of bonded atoms. So that's why repulsions will be more, will have higher energy. So the electron present in the bonding orbitals result in the attraction between two atoms. Here, you know, bonding means what is attraction. So here, you know, bond will not form, so that's why repulsion. The electron present in anti-bonding orbital results in the repulsion between the two atoms. Repulsion means bond formation will not take place here, takes place. Bonding orbital, you know, bonding molecular orbital have lower energy than atomic orbital. Diagram I have written. Atomic orbital down, bonding molecular orbital up, anti-bonding molecular orbital. That is only. And these are, you know, anti-bonding molecular orbital have higher energy than the atomic orbitals, and they are formed when the lobes have same sign. I already said lobes have same sign. Then what will form here? You will get the so this is I mentioned molecular orbital. Same sign overlapping bonding molecular orbitals and different sign, opposite sign, anti-bonding molecular orbital. And they are represented by which one? Sigma and pi. Bonding molecular orbital, anti-bonding molecular are represented by sigma star and pi star. And this is what is the difference between the bonding molecular orbital and anti-bonding molecular orbital.